Hi everybody. So let's discuss a little bit my handout for the True Parallel RLC circuit. I give you 3 pages of my handout, which has some information for you, some hints, some helpers. Here we have the current, the circuit. The real circuit we have to calculate with all the parameters, the questions in red. I gave you already the currents with opposite directions. Why? Because the inductivity and the capacitance are opposite to each other. That means the current on the capacitor leads the voltage, on the inductance it lags the voltage, therefore it should have different directions. When you analyze the circuit, this is a little bit this one here and this one, you realize, oh, this is the circuit for an electrical motor, which is compensated by a capacitor. The capacitor is there in order to correct the power factor. I gave you also what would be the correct value for the capacitance so that the voltage and the current is in phase. You have no reactance power, but the power factor issue is a different lesson. This one here gives you the requirements, what you have to know already, how to do vectors, complex numbers, what is Kirchhoff's law, what is Ohm's law, what are the features. These are the features of all the different components we use, the resistance, the inductor, and the capacitance. And you will see also that I gave you, okay, the current on an inductor leads by 90 degrees behind the voltage, or on the capacitor on an inductor it lags by 90 degrees behind the voltage, and on a capacitor it leads by 90 degrees the voltage. Then here is some other helper stuff. When you want to do mass, how to convert vectors from Cartesian rectangular into polar coordinates and back and forth, how to do addition, vector addition, how to do multiplication, the same for the division of vectors or complex numbers. And then also important to know when it deals with omega, which is our 2 multiplied by pi multiplied by frequency, how to convert into radians when you have the angles in degrees, because most of the time when you calculate the sine or the cosine of something, you need the radian and not the degrees. You have to check your calculator how to set it to degrees or radians. And this one here is really auxiliary. It talks a little bit about the power factor, which is not part of this lesson, which is a different one. It tells you when you have a receiver with an impedance, the best way in analog and digital logics is to have an impedance matching, so that the receiver impedance is connected with the same impedance of the cable to the source, which gives you a power factor of 1. That means there is no ringing. That means you have no reflections, no signal distortion. Everything looks much better. If you don't have impedance matching, then you get a lot of reflections and the signal looks really, really odd. And the power distribution is a little bit different. We want to optimize for the minimal loss over the cable, but this results in the fact that the reactive power matters a lot. If your receiver has a lot of reactive power, that means your source has to provide also the reactive power, not just the effective power. That means, or the real power. It means it has to provide also the reactive power, because of your consumer of the power is not really in phase with the voltage, so that you lose a lot of, I wouldn't say power, but you will draw a lot of current from the power source, and therefore the power source has to be able to provide this. Okay, this is page number 1. Let's jump to page number 2. Here I give you the options to calculate the current through the True Parallel RLC connection or circuit. You have option number 1, you calculate the entire impedance of your circuit, and then you use Ohm's law. This is Ohm's law in order to calculate the current. And then when you have this one, you would know, okay, what is the function for the current dependent on the time, which is this one. It's a sine wave. It's the magnitude of the voltage. It's the magnitude of the impedance. And the impedance has also a phase angle, and the phase angle is represented here, so that you can calculate, okay, the current at this time is dependent on my difference between the angle of the voltage and the impedance. Or you go this way, Kirchhoff's law, which is a little bit easier. In this case, because we need just the current, and at the end we get the current, we could convert the current into a impedance and then use the way via the impedance, but we have already the current, because the current is already the sum of both, the current of both branches. In order to calculate the current of every branch, it's given here. That means it's also again Ohm's law. And at the end, you get a phasor diagram for all the currents. And you see, oh, okay, we have a little bit large inductance or inductivity. That means our phase is a little bit negative. It's not really completely compensated by the capacitance. And you see here all the values. And then the other question was, what is the current when our voltage reaches the 60-degree phase angle? And I give you here a drawing, and you see, okay, the current lags behind, so that we can use the phase difference between voltage and current, and then we use this formula in order to figure out, okay, what is the momentary current at this point when the voltage reaches 60 degrees of its phase. The very important thing to be in mind is everything what we done before is based on the voltage given us on the schematics, but in the schematics the voltage given us is in RMS. It means it's the effective voltage. It's not the peak voltage. It's not really the maximum peak we can reach. It's just the effective one, the RMS one. Therefore, all our calculations give us also the effective RMS current, so that we have to correct. And the correction is by the square root of 2. It means before you do really the final result, you have to bear in mind, at some point we have to convert the effective RMS voltage or RMS current into a real or full peak voltage or current, and it gives us at the end this one. Okay, here again 60 degrees voltage. We have a phase shift of minus 9.45 degrees. The current lags a little bit because the inductivity is a little bit larger than the capacitance, so that we have at the end a phase difference, and this matters here in order to calculate the momentary value. The last page is just a graph created by a Python script. This is a Python script result in order to show you, okay, what we have. We have the real voltage here. Everything is already corrected for the peak voltages, not effective anymore. That means the real peak voltage. And then we want to figure out, okay, what is the momentary value of our current when the voltage reaches 60-degree offset. You see in the graph already, okay, this should be a little bit less than the maximum. This would be the maximum here, maximum current. And then you figure out this value. You can use the formula or you can use the graph and measure on the graph. What you figure out also that the currents in the different branches, the red one is for the RL branch. You see it's pretty high. For the capacitance, which is the green one, is also pretty high. And there's a cross-check, and the cross-check is in such a case that you have a parallel inductance with a parallel capacitor. The current, the sum of the current must be lower than the maximum of each of these branches, either of these branches. That means it cannot be higher than this value or this value, or that this value must be lower than the other two values, because both currents are in opposite to each other, so that the resulting current is lower than the single current in one of the branches, because we do the summary. Let me go back to this page. Here you see, okay, these voltages, these currents are opposite to each other. This one here, the current through the capacitor, it has a different direction than the current through the resistor and inductivity branch, so that the resultant one must be, first of all, smaller, and the angle must be smaller. The angle actually depends at the end just of the real resistance in the serial branch with the resistor and the inductor, but it's still a little bit negative. That means the current lags a little bit behind the voltage. Okay, this is the result or the interpretation of my handout. I give you all the requirements. I give you the task in the beginning. What is asked for? We want to know what is the function of the current and dependent on the time. And then also the other question is, what is the momentary value of the current when the voltage reaches 90 degrees? Some helpers, prerequisites, what you should know. Some mass helper, how to convert between Cartesian or rectangular into polar coordinates. And it's this one, this is a little bit auxiliary to understand, okay, what does it mean? Why this circuit is so important, or why do we have to know what is impedance and impedance matching and power factor and all this stuff, but this is a different lesson. Okay. The second slide, nothing special. And that's all. Thank you very much.